The obvious limitation is that if you patch some data in the program, then the program might try to read it or write it, and it might override your jump instruction, thus rendering it invalid. This doesn't happen very often in compiled code because the compiler doesn't really use the same bytes as code and data, but if you have a packed or somehow protected application, you might get into this case. The other limitation is that the 5 bytes that you overwrite cannot cross a basic block boundary. This means that nobody else in the program should jump into the middle of these 5 bytes, because if they do, they will jump into the middle of your jump instruction, and most likely the program will crash. Another limitation, if you're doing the patching while the program is running, that's not a problem if you're patching it before the program starts. But if you do it after the program is running and you have a call instruction and you override the call instruction and the bytes following it, your jump instruction might coincide with a return address that's saved on the stack. Because if that call instruction was executed previously, the program might be somewhere in the callee, and on the stack it'll have the address after the call instruction. So if you do the patch now and then the program returns back to that address, it will return into the middle of your jump instruction, and again it'll most likely hit an invalid code and it'll crash. For the same reason, you should not have int instructions or sysenter instructions in your patch area, because the program might be executing a kernel call, and then you do the patch, and then the kernel returns after the int instruction and lands into the middle of your jump instruction. In most cases, these things are not really a problem. Static analysis with IDA Pro is sufficient to find if a patch point is suitable. And I actually have a small IDA plugin that looks at a patch point and just tells me whether it's good or bad. Microsoft also has a hot patching implementation. It is used only in Windows 2003 Service Pack 1, but we'll probably see more of it in Vista and Longhorn. Because they have control of their toolchain, including the compiler, they took a slightly different approach than the third-party hot patching systems that we talked about earlier. In Visual Studio 2005, there is a new compiler option called /hotpatch, which adds the move EDI instruction in the beginning of every function. This is a 2-byte instruction that basically acts as a no-op. Also, if you use that compiler option, every instruction will have 5 bytes of padding before it, padding that is not used. When the Microsoft hot patch is applied, it replaces the first 2 bytes of the function, which are the move EDI instruction, with a short jump back to the padding. Then it puts a 5-byte jump in the padding area that goes to the hot patch DLL. This allows Microsoft to replace one function with its patched copy. While most of the other third-party patches limit themselves to just modifying a few instructions or maybe modifying a little bit of data and then returning back to the original function, the Microsoft hot patching implementation actually completely replaces the function. And what's most interesting is that they appear to have an automated tool that generates the hot patch by comparing the original and the patched binaries. And they can do this, they have the ability to do this because they have access to the private debugging symbols and the source code, which makes this kind of thing much easier. One limitation of the technique is that they have to replace the entire function. They cannot do something small. And they still have the same problems that everybody else has, which is if the problem requires an extensive redesign of the application or a change in major data structures, then their hot patching technique just can't deal with that. I think the biggest limitation of the technique is that it requires compiler support. If you have code that is not compiled with the /hotpatch option, then they cannot hot patch it unless they resort to other techniques, such as the ones we talked about earlier. And I think right now, Windows 2003, the latest versions of most of their operating systems are compiled with /hotpatch if you disassemble the files, but only Windows 2003 Service Pack 1 has patches that were released with hot patching support. And before we get to this, I have a short demo. I wasn't sure if I'll have time for it, but I think I do. Just in case anybody thinks that hot patching is like the brand new thing, here's a little thing. I think it's kind of cool. This is DOS 3.30 from 1987. And we're going to use the debug command to look at the interrupt handler for interrupt 21. This is the interrupt that DOS uses to execute it, that programs use to call the DOS system functions. And to look at the interrupt, we need to look at address 84, which is in the interrupt table. And the first 4 bytes that you see there, I hope you can see that. The first 4 bytes are the address of the handler that handles that interrupt. And this handler would be DOS code responsible for executing the system call. If we disassemble the code of the address, which is here, we see that basically it's a big switch statement on the AH register, which contains the number of the system function that we're calling. So this is what the code looks under normal circumstances. Now we're going to run the Frodo virus, which was, I believe, written in 1988, and it was a fairly advanced for its time virus. It had very good stealth capabilities, and it's also memory resident, which means that it stays in memory and it intercepts interrupt 21, and whenever you execute a program, it infects it. If we look at the interrupt handler again, we'll see that the address, the first 4 bytes, have not changed. And this is kind of unusual because usually in DOS, if you want to modify an interrupt handler, you would just replace the address in the interrupt table, and then your code will get executed. But this is not what the virus does, and it's part of a stealth technique to make it harder to detect. If we disassemble the DOS code, or the place where the DOS code used to be, we'll see that its first 5 bytes have been overwritten with a jump instruction going to the virus body. So the virus will execute its thing and then jump back to the original DOS handler, just like I showed in the slides earlier. So I just thought it was kind of cool. All right, so let's continue with the talk. In the third part, we'll go over some of the vulnerability analysis techniques that you need to use if you want to generate these hot patches. To some people, developing patches without having access to the source code seems like black magic, but it's actually not that hard. The process that you have to use is actually very similar to the exploit development process. Usually, to develop an exploit, you start with some kind of request or a file that is malformed and crashes the application. You would run it in a debugger. You would find where the application crashes. Then you would use IDA Pro to reverse engineer the code around the application code around the location where the crash happens. You would try to find out what causes it. And finally, you would write the exploit to take advantage of that crash and make it do something useful. The hot patch development process is very similar. Instead, in the last step, instead of writing an exploit, you end up writing a patch that fixes the vulnerability. So here's a collection of a few tricks. This is not organized in any particular way, but I just have a few tricks that I use to debug various kinds of vulnerabilities. If you have a Stack Overflow, and you run it in the debugger, usually you're going to see a crash. If you have a full exploit that executes shellcode, then you're not going to see a crash. But in that case, you can replace the return address that's in the exploit code with an invalid address like 0, and then the program will crash. Or another alternative is to turn on DEP, which will cause the debugger to break in when you get to the first instruction of the shellcode, assuming that the shellcode is on the stack or on the heap. So once you find where the crash is, you want to look at the call stack and see how we got to that place. One problem is that stack overflows usually override a bunch of the stack, and you can't see the call stack anymore because it's overwritten. So to work around that, the solution is find the minimum size of the request that causes the crash without overriding anything past it. So if you do this, you'll have a request that overrides just the return address, crashes the application, but the call stack that's above that will stay not corrupted, and you'll be able to look at it. The last return address on the stack will point you to the parent function of the function where the overflow happened. So once you have that, you can put a breakpoint there. You can trace through the execution, find the location where the vulnerability is. Heap overflows are a little bit harder to debug because there's usually a large gap between the time when the heap is corrupted and the time when the heap corruption actually overrides something useful. One solution is to use the debugging heap in WinDBG to spot heap corruption early on. I think this only works in XP Service Pack 2 and maybe 2003. If you know what location, if you have an exploit that overrides a specific location, like one of the pointers in the PEB, you can put a hardware breakpoint there and you can catch the write to that location. Once you have that, you can look at the call stack, and most likely the override happens in a free function, so you have to find out who calls the free function and on which memory block. Then, if you have a log of all memory allocations that happened before that in the program, you can match the block that is being freed against your log file and find out who allocated it. Once you know who allocated it, you can use reverse engineering techniques to figure out what this block is supposed to be, what it's used for, who frees it, who allocates it, and so on. There are a variety of methods for getting heap logs, but one that I use is these two conditional breakpoints in WinDBG that patch the free heap function and the allocate heap function, and basically they just print that there was a request for this many bytes and it resulted in this buffer, and they print the address of the buffer. And same with the free function. If you have an uninitialized variable problem, you have to find out what this uninitialized variable was supposed to be used for and who was supposed to initialize it.